The intersection of two equivalence relations on a set is an equivalence relation on the set. Okay, let us try to understand the problem first. So here, it's given here that we have two equivalence relation, and if we take the intersection of those two equivalence relation, then we are going to get a new relation which is also a equivalence relation. Okay, so let's do one thing. Let us consider two relation R and S which are equivalent relations on a given set A. In other words, we have the relation R, which is a subset of the Cartesian product of the set A with itself, and we have the relation S, which is going to be a Cartesian product of the which is going to be a subset of the Cartesian product of the set A with itself. Now this must imply that if we take the intersection of the two relations R and S, then R and S must be a subset of the Cartesian product of A with itself. This is what we need to prove. Okay. Now, in order to show that R intersection S is also an equivalence relation, so it must be reflexive, it must be symmetric, and it must be transitive. So let's check for reflexivity first. To check for reflexivity, we'll consider an arbitrary element of the set A. Then, in that case, if we say that A belongs to the set A, it must imply that the ordered pair A comma A must belong to the relation R, and the ordered pair A comma A must also belong to the relation S as well, because it's given here that R and S are reflexive in nature. They are reflexive relation. Now, we can combine this statement and we can also rewrite it as the ordered pair A comma A belongs to R and also belongs to S, which means that the ordered pair A comma A must belong to, now what does it mean when we say R and S? That simply means R intersection S. So here we have shown that for an arbitrary element A belonging to the set A, if A comma A, the ordered pair belongs to R and the ordered pair A comma A also belongs to S, then it must be true that the ordered pair A comma A must belong to R intersection S. So thus we can say thus the ordered pair A comma A belongs to R intersection S for all A belonging to the set A. So we can say, so R intersection S is a reflexive relation. This is a relation, but it's also going to be a reflexive relation on the set A. Okay, so we have tackled the first part. We have showed that R intersection S is a reflexive relation. Next, we will check for symmetry. Now, to check for symmetry, we're going to pick up two elements. So let's say we are going to pick up the elements A and B from the set A. So A comma B belonging to the set A such that the ordered pair A comma B belongs to R intersection S. So we're considering that we have an element A comma B picked up from the intersection of the relation R with the relation S. Then what does it mean? Then A comma B belonging to R intersection S simply means this simply means that A comma B belongs to R and the ordered pair A comma B also belongs to the relation S. That's the definition of an intersection. An element must belong to both R as well as S. Okay. However, if A comma B belongs to R, can we not say that B comma A also belongs to R? Similarly, we can also say B comma A belongs to the relation S. Why can we say that? Because it's already given that R and S are symmetric. If R and S are symmetric, then from symmetry it must follow that if the ordered pair A comma belongs to one of the relation, then interchanging the elements within the ordered pair, that means B comma A must also belong to that relation. Now we can combine this statement as B comma A belonging to the relation R as well as the relation S, which implies that B comma A belongs to R intersection S. Okay, so we started out by considering A comma B belonging to R intersection S, and we showed that B comma A also belongs to R intersection S. So here we can say that thus thus A comma B belongs to R intersection S implies that the ordered pair B comma A also belongs to R intersection S and is going to be true for all values of A and B belonging to the set A. So here what we have shown, so here we have shown that the relation R intersection S is symmetric. This is a symmetric relation. R is symmetric relation on the set A. And finally, we will check for transitivity. To check for transitivity, we are going to suppose three elements. So let's say those three elements are A, B, and C. And we're going to pick these three elements from the set A such that we are considering that the ordered pair A comma B and the ordered pair B comma C, both of them belongs to the intersection of the relation R and S. Then what does it mean? So if we say A comma B belonging to R intersection S and we say that B comma C also belongs to R intersection S, our goal will be to show that A comma C also belongs to R intersection S. So let's try to check whether if this is true or not. Now what does it mean when we say A comma B belongs to R intersection S? Now A comma B belonging to R intersection S simply means that, so here we can say that A comma B, this is going to belong to R and the ordered pair A comma B is also going to belong to the relation S. Similarly, B comma C belongs to the relation R and we can say the ordered pair B comma C also belongs to the relation S. Now what we'll do, we're going to rewrite this statement. We're going to take this and rewrite it as A comma B belongs to the relation R and A comma and we have B comma C belonging to the relation R. And then we're going to combine these two statements and rewrite it as A comma B belongs to the relation S and we have B comma C belonging to the relation S as well. Now we know that the relation R is transitive. That's already given to us. So what does it mean when we say a given relation is transitive? So it means that if we have A comma B belonging to R and B comma C belonging to R, then it must be true that A comma C must belong to the relation R. And similarly, we have the ordered pair A comma B belonging to S and B comma C belonging to S. So that means that A comma C belongs to S as well. Now we can combine these two statements as A comma C belonging to R and S. Or we can say the ordered pair A comma C belongs to R intersection S. So here we started out by considering the ordered pairs A comma B belonging to the intersection of the relation R and S, and we consider another ordered pair B comma C belonging to the intersection of R and S, and this implied that the ordered pair A comma C also belongs to the intersection of R and S for all values of A, B and C belonging to the set A. So this means that we can say, so our relation R intersection S is also transitive. This is a transitive relation, on R intersection S. So what we have done, so we have shown that our given relation R intersection S is a reflexive relation on A, it is a symmetric relation on A, and it's also a transitive relation on A. So therefore we can finally say hence that R intersection S is an equivalence relation, relation on the set A, provided R and S are also an equivalence relation.